Ah, yes. Now the moment comes where I actually have to go live. I did this to myself. Um, I do not have my scenes in order. Where are we going? Huh. Guess we'll just go to this one. um, excellent. Already running into problems. Scene that is supposed to be there is not. Anyways, yeah. So now we get to see that I have not addressed a camera in, at least in English. In college, I had to do stuff for Japanese, but not addressed a camera in good time. Man, what is the story here? I guess I should tell this story because it is a very me story. Yeah. So this morning I was advising a colleague on what to do to prepare for a lattice cryptography course next year, and we got to talking about computational hardness and hard problems. And it's just kind of interesting explaining to someone how, say, the Diffie-Hellman problem works and how to construct it so that's hard is very difficult because it's very abstract, and when you try to instantiate it into the integers, it gets even worse. But it is the easiest sort of problem to turn into an effective cryptographic scheme, and this is oft exploited. However, lattice cryptography is different in that it's very difficult to explain how to turn it into an effective cryptographic scheme. However, it's very easy to explain what the hardness of the problems on lattices are, because it's very geometric and speaks to the intuition. But one of we started talking about sort of more classical, not quantum hard, but just sort of MP complete problems, and one of them that came up was exact covers. And that sparked an idea of, well, I didn't plan to finish this puzzle any other way, so why don't I review exact covers, and in particular exact hitting, as it applies to Sudoku. So the story of this puzzle, how this puzzle came about. This is just a one of the puzzles that Cracking the Cryptic did, and IU picked it up on her Twitter, and I thought I'd give it a shot too. That was a mistake. So this puzzle is interesting. It has your sort of normal standard Sudoku constraints. We have these gray boxes which act just like the normal Sudoku boxes, so they're just a typical cage constraint, nothing too amazing there. But why I thought this would be like a good problem to approach computationally is because we have a good variety of additional constraints. We have these sort of typical cage constraints, which are not super interesting, but at least give reason to be a bit more agnostic as to what kind of cage constraints we allow in our solver. And then we have the second rule that cells separated by knight's move in chess cannot contain the same digit, which is a very simple rule to say, and it's also not a particularly difficult rule to compute with either. What it does end up doing is just end up being a large number of intricately intertwined exact hitting constraints. And so that's interesting in the sense that it's not going to add a different type of constraint to the problem, but just the number of ways that numbers can clash in this sort of nice smooth pattern encourages some sort of like pre-generation and constraint generation step to our solver. So that'll be interesting. And then we have this third rule that digits along an arrow must sum to the digit in the arrow's circle. Arithmetic constraints are the worst because they are not exact hitting constraints and they work very differently than other usual Sudoku constraints. And I did not like this constraint. I prefer, so it's not unusual to have a Sudoku like this that has no numbers in it to start. And you will usually get some sort of constraint that is not an exact hitting constraint to help you actually start the problem. In this case, we get this arithmetic constraint. I much prefer order constraints. They're just much easier to work with, much easier to think about. And I'm kind of curious to see how much backtracking our solver ends up needing to solve this puzzle, because I tried to satisfy this arithmetic constraint for quite a while, and I was not able to figure it out with pen and paper. I am very lazy in Sudoku about doing any sort of guess and check backtracking. So if it required that would be the reason why I didn't figure it out. But you can get some sort of like easy wins. Like these are all three numbers summing to one number, and they're all within these cages, so they all have to be unique. And so you can limit it to sort of like 20-ish, I think, unique triples that can be here. And it leads to only 4 different numbers that can be in these boxes, and that gives some sort of interaction with the other constraints that could maybe help you figure it out. But I wasn't able to actually end up satisfying that constraint, and solve the puzzle, and eventually got to the point where I was basically doing a shorthand form of algorithm X on pen and paper, and like at that point I'm not really solving the puzzle, I'm just doing it. And so I was like, if this puzzle is gonna make me go to that point anyways, because that's my level of patience for backtracking, or maybe I'm just stupid and didn't see something that's quite a possibility, then I might as well go all the way and just write a solver. So I'm gonna start with we're gonna start with something that maybe doesn't seem a whole lot to do with Sudoku to begin with. Let's see. I should still... One second. It would be wise if I still had the stream up. There we go. Okay. So, hopefully I am not muted. That would be embarrassing, and I can't check Streamlabs because I don't have a second monitor. This streaming setup. Ooh, this is really scuffed. Okay. So let us discuss what will eventually become our algorithm. So we have a, and let me pull up my notes real quick so I can hopefully get through this a little bit faster. Don't make this too boring. So the exact cover problem is we have a set S, and we have a set X, yes. And I'm trying to figure out how to express this in a logical relation. I guess we could just say we have that X is a subset of S. And the problem is to find in S star such that writing constraints on the fly is hard. Every element of S star is a subset of S, and for every element of X, I could even put a wedge here. For every element of X, there exists a unique S in S prime, or S star rather, where where A is an S, or sorry, B is what I used here. Where B is an S. Okay. So this is sort of a formal definition with some constraints. To break it down a little bit with an illustration, I like to think of this problem as a function reversal problem, I guess. And the reason why I like to think about it is it's actually a more complicated way of explaining it in terms of set theory, but it leads to a nice sort of diagram. So what we'll have is we will have this is our set X. Maybe like this. And then this is not, well, I guess you could call this, sure, you could call this, I feel like this is normally called, this set here is called S. I'm gonna have to call it something else. I've made a mistake in my convention here. I've made S our like alphabet. So let's introduce P. Actually, I screwed this up. We'll make this the power set of S. That's fine. We can do that. And so you have this has to be a subset of the power set of S, does it? Let's call it, I don't want to get it confusing by calling it P. Y, sure, why not? Y is a usually proper subset of the power set of S. There we go. Okay. The scuffness of this setup is already becoming apparent. It's great. Gotta love it. So we have these. So S is our sort of like alphabet that X can be from. Frankly, I just shouldn't have bothered with S. Let me move over a little bit. Let me just get the conventions right here. It'll make it less confusing going forward. So we have X, and we have S, and S is such that it's every element is a subset of X. So for all S in S is usually proper subset of X. If it's not, there's a trivial solution, but that's okay. And we want to find an S star such that S star is usually proper, but doesn't have to be, subset of S, given that for every element of X, there exists a unique set S in S star containing this element of X. Okay. So those are our formal constraints. And basically what this means is we have these sets of the set of elements X, and we have some choices of subsets that we can pick from X, and that's S. And we have to pick some of those so that every element of X is in one of the subsets that we choose, and that it's in only precisely one of the subsets that we choose. And so we can draw this out in a sort of like function set format. And let me clean up. Let's see, this is going to be off screen for you all, but I'll clean up the garbage mistake I made up there. And then we don't have to do this Y stuff now. We can just, it can just exist. It can just be S. So maybe, so S is a collection of subsets, a set of subsets of X. And so maybe we have like one subset that contains, so what I'm doing here is I'm drawing a relation, right? This is a relation diagram. And this relation is going to be between the sets in S and the elements they contain in X. So maybe this one contains these two. Maybe this one contains these two. Maybe I don't want to make this diagram too confusing. should probably be using colors more than I am, but I'm not going to. Then maybe that one has 3 elements. And maybe that one has no elements. I'm just feeling lucky, right? This one, and I'm already seeing a potential cover, so I'm just going to complete it really simple like that. So we have this relation, and specifically this is the relation R is equal to, let's see, I don't want to express this in set builder notation because I'm going to get this. I should probably not put an equal sign here because whatever I'm about to write is not going to be equal. This relation is expressing the idea that an element x from x is contained in S. So in x from the set x and an S from S. Make this. There we go. And this relation is expressing the idea that the given set in S contains the element in X. And the idea, an example of an exact cover is if I, man, I do not know Excalibur. If I were to say take this one, so this set contains this element, and then I could take this set, which contains these 3 elements. Actually, this is an opportunity to color code. Let's do it. Got to take the low-hanging fruit with the colors. Okay. There we go. It will be a code stream, I promise. We're getting there. I do not code without math. You should know this about me now. Trust me, before I'm yelling at you about security stuff on ping, I'm drawing out architectural diagrams that are about this mathy. And then we can choose, say this one. And then we will have, I gotta see where I should be drawing this. Maybe over here. You'll be able to see that. So now we have the set S star being equal to, and I'm just going to use colored dots to represent these. So each of these dots are sets because S is a set of sets. Some code can be anti-math, and I hate it. I'm very much of the opinion that once you learn to digest it or have someone make it digestible for you is fair. Math makes your code better. That's what I found. All right. So you can have honestly say you can regret every time I brought math into your code. That's because you're bad at math, not because the math had anything to do with it. Math's too much for you. Adderall is fine, but math is just a step too far. It's fair. Okay, so we have S being a set of sets, um, and we picked some of them. The green one, which has the two elements. If I'm careful, I can indicate. Actually, it's not doing it anymore. Oh, it's just Excalibur was really slow about it. Okay, that's fine. Um, so we have a set in S, this green set that contains the two green circled elements of X, the orange set containing the three orange circled elements, the red set containing the red circled element, and the output of our algorithm, if it works correctly, the point of the problem is to output a set that would contain, for example, these three sets. And the reason why these three sets form an exact cover is because they are a cover in that one of the sets is certain to contain, each element of X is certain to be contained in one of the sets of S, and that makes it a cover, and it's an exact cover because only one set in S contains every set in X. This is almost, it's not quite, but it's almost what a Sudoku puzzle is when you express it as math. It's not quite if you try to think about it, unless you figure out the exact hidden conversion. It's not going to be immediately apparent that this has anything to do with Sudoku. So now I have a choice here. I can go into how do we turn this into something useful for Sudoku, or I can go to how we'll actually go about solving this problem in code. Let's talk about how we'll go about solving this problem in code, just because it's on my mind and a bit more accessible. So we have this relation, right? And I mentioned this is kind of like reversing a relation, because once you have an exact cover, then if you restrict this relation's domain to that exact cover, then the relation has an inverse function. Even though the relation is not a function, even when restricted to the exact cover, it has an inverse that is a function. So in that sense, it's sort of constructing this inverse relation or inverse function. And it turns out that exploiting this for our code is going to be useful. So there we go. Excalibur is almost too intuitive. I expect it to not work like most software, and then it just does. Okay. So if you imagine for a moment, it will be useful to us to have a numbering, some order on the elements of X and S. So I'm just gonna go down and order this 1, 2, 3, 4, 5, 6, and so on. 1, 2, 3, 4, 5, 6. So perhaps not a surprise from graphs, we can also represent relations as matrices. And so if we were to do that with this relation, we might call this, I've made this a little bit too close. I could move it because this is Excalibur, but I'm not going to. We just go for it. Let's call this the S dimension. And I'm probably not using conventional direction for notating elements of matrices because I forget which way is which all of the time. And then I also know it starts from 0, and I have not. I have chosen the Lua convention here. We'll make this our x dimension. And then we can create an incidence matrix. And so to do this, we will look at where, for example, if I can bring out some more color here. Color is always good. I don't do ML, okay? That's the one... You know when I said I can do everything in software engineering, that's the one exception. I don't do ML. Sorry. Actually, this is Excalibur. I can probably just change the color of lines. That's crazy. Okay. That's a thing I can do, right? Like I can just select that and make it blue. Boom. Easy. So I can create an incidence matrix. Now that I think about it, doing like some sort of OCR on the the actual puzzle page is like probably not too hard. I don't actually think that's useful, but I could do it. So for each I guess these are technically elements of the relation. I don't like the terminology because it confuses people that don't know set constructions, but they are technically elements of these lines are elements of the relation. And for each line, I can put a 1 in the corresponding place in the matrix that corresponds to the element of S and the element of X that are paired in that element of the relation. So this will be the first one, So we'll put a 1 up here. Let's choose another element of... The Brain Age DS speedrun is very good. It's very good. Yeah, I have a lot of appreciation for how much just work probably went into doing all the RNG manipulation. I mean, obviously all scripted. It's code generation, but still impressive. So that purple element is between S1 and X2. I mean, to be fair, you have to give Brain Age the credit there. I don't think you could... I can't imagine how a game could have a higher tier of possible RNG manipulation. And then I'm not going to do the whole thing, but just to do a third example. This one. So this is between the third element of S and the second element of X. So I could put a 1 here. Let me just quickly... I don't want to just like fill it in with zeros incorrectly because that could be confusing. So I will just quickly do the rest of the elements of the relationship. So we have a 2 to 1. We have a 2 to 3. Yes. We have 3 also to 4. And 3 to 5. And 4 to nothing, of course. And 5 to 6. I have to make sure that this table will actually line up when I'm done with it. And a 6 to 5. Okay. And the rest will be zeros. I feel like my table has magically become wider. That's because I put an extra row of zeros. I am the best. I know exactly what I'm doing. Don't let anybody tell you otherwise. Oh my goodness. I should have warned you beforehand that this stream was just going to be, something to make customers question our dedication to quality, and nothing else. Okay. So this is what an incidence matrix for this relationship would it look like. And the idea is this seems sort of, when you look at this diagram on the left and then you look at the matrix on the right, it looks kind of like we've lost some efficiency in the representation. And in a sense we have. Certainly it's a lot easier visually to look at this left thing if I drew it with neat lines in Illustrator and not with my shitty drawing abilities. But we can get some intuition about what this relationship might be on the left, and on the right it's just kind of it's numbers. But the nice thing is if you want to ask, is X related to S? Or I guess it should be the other way, S related to X, but whatever. We're not quite super rigorous with the relation stuff over here. Then all you have to do is go to the corresponding column of X and a row of S and ask, is that element a 1? And if it is, then they are related, and if it is not, then they're not. So this is actually a very efficient way of computing relations. Maybe not the most efficient way of storing them. But there's another interesting property about the incidence matrix, which is that if you say we're gonna get fancy here. I'm gonna use the box tool. Oh no. It might break everything. Stand by. If we look at, say, column number 4 here, we'll notice that it only has 1 1 in it. And this is an example of a case where if a human were solving a Sudoku puzzle, they would be able to make a deduction here, in that because there's only 1 1 in this column, only one set in S contains that particular element in X. And so this set 3 has to be in our exact cover. And so we can know that 3 is in our exact cover. There's actually 2 columns here that are like that. But let's say none of our columns are like that. So we're not gonna use column 3 or column 4. That's too easy. That's no fun. What if the best we had is, say, like column 5? It has 2 sets. The 2 sets that could contain it, that we could put in our cover. And the question we have is, which set do we choose? Which set is going to be in our cover? And I don't know. Did I mention that this is an NP complete problem? That might give you a hint as to what we're going to do here. It turns out that a perfectly fine way to try to figure out which set should belong in our exact cover is to just guess. just guess one. It doesn't matter. Pick one. It does matter, of course. We could lock ourselves into a particular spot. For example, if we were to pick, what would a set that definitely couldn't be undercover be? I feel like 6 would be problematic. Why would 6 be problematic? Maybe 6 is fine. I'm not seeing any immediate problems. But the point is you can pick wrong. You can pick a set that when you put it in your cover, ends up creating a partial cover that cannot be completed into an exact cover. And all you do is you backtrack up what will eventually sprawl out into a search tree. You just backtrack up and guess a different thing. And there is no better algorithm that we know of for solving this. There's optimizations, of course. If we have these sort of deductions where we can deduce that a particular set has to be in our cover, then we probably should take advantage of that. And we also have, our observation of say, picking, we don't have any column here that has 3 ones in it, for example. But picking a column that has 2 ones over a column that has 3 ones is just higher chance of being right the first time because there's less options. And so you can make that sort of optimization, but in general, this algorithm is going to be exponential time. There's not a sub-exponential time algorithm known for this problem. And that is just the reality of it. And that is it's a philosophical point that keeps me up at night. We think of Sudoku as a puzzle of deduction, and it turns out that this is true in most of the within the realm of puzzles that we actually make and solve as humans. But fundamentally, the problem with Sudoku is just guess and check. And it's the desire to create puzzles that are fun and engaging that leads us to create puzzles that have lots of these one possible constraint columns in it. So when we pick a set and we have this element 4, we figured out that only 3 is the only set that contains it, so we know that our set 3 is going to be in the cover. What we do before going on to the next step is we just say we don't need to consider 3 anymore because it's already in cover. We decided we're going to use 3. And we're also not going to consider 2, 4, 5, because those elements are already contained by sets in our cover, so we don't have to worry about them. And so now we have this new instance matrix, which is much smaller. That looks like, and y'all will still be able to see this. I have to move quite yet. Looks like this. So we have 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, 0. And this will only have a subset of the labels. Oops, this should be 6. Yes, 6, 0. Okay. And so now we can perform the same thing, look at the columns. In this case, we again have deducible constraint solutions, but if we didn't, we would just pick one that's small, that has a small number of possibilities, like this element 1, and just randomly choose one, try it, see what happens. If it works, great. If it doesn't, again, just go back up a search tree until we get back to this and choose the other option. Of course, well, I guess it won't be a problem. You can only delete, say, we chose set 3 for the purpose of set 4, right? So you could only delete column 4 if you wanted to. But then you have to be careful that you don't choose a second set that has the other columns in it. In general, that's something to worry about. For example, and we could actually implement this in our solver if we wanted to go a step further, which I don't know, sounds like a good idea to me, is we could actually deduce from this step that we also can't have 6, yes, because we chose 3, and if we chose 6, we would have a double cover of element 5 from X. So you could have that sort of thing happen. And again, similar reasoning. Yeah, I think it's the only additional deduction we can make. 3. I thought there was something with 2, but yeah, there is. We have 2, so we also can't have 1 in our cover. So we could get even smaller. We could, from the same step, go to this sort of rectangular matrix, or by making sort of additional deductions, we could get even smaller to this matrix right here. Oh, it looks like it's a little bit off the screen because I'm writing it big. Like this. The numbers got bigger than 3. Well, they're about to go to like 800, so hold on for a second. And so the elements that will remain here are 1, 3, 6 on the bottom again. But we've actually rolled out some choices of sets. We have 2, 4, 5 remaining. And then, of course, at this point, the cover is trivial. We can see it's 5 and 2. And that gets you the full cover 2, 3, 5 that we had earlier. Up here. 2, 3, 5. So that is the general algorithm. It's not super clear, but it works. And yeah, so the question is, how do we apply it to Sudoku? Because these set cover constraints are not Sudoku constraints. If you try to fit them to Sudoku constraints, it actually won't work. You'll run into some issues. But a key insight that you might have is that we're choosing sets from S to be our sets in our cover. And so a question we might ask is, what if we just have S be the set of choices that we make when solving the puzzle? So if we have, I'm going to make this, okay, I'm going to try to center this so that our screens are about the same and I won't screw this up. So if we imagine we had our set S, and it's just a very big set, and our set X, and in S, we're going to have the choices that we make during solving a Sudoku puzzle. So we'll start with just a simple puzzle with, and it turns out this is going to be extended to any puzzles with so-called exact hitting constraints, which is not completely the puzzle that we're going to be solving, but that's a detail for way down the road. Let's consider a normal Sudoku puzzle for now. A choice that we might make is that, and the exact numbering of the rows and columns don't matter here, but we might choose that the cell in row 1 and column 1 contains the digit 1. And we could choose that it contains the digit 2. And we could choose it contains the digit 3. And so on. And then we'll get to row 1, column 2 could contain the digit 1. Or it could contain the digit 2. And we keep going. And eventually we finish the row. We get row 1, column 9 could contain digit 9. And then we go to row 2. Row 2, column 1 could contain digit 1. So of course we have the order of our set S. There we go. Let me zoom out just a tad. Just a tad. Just a tad. There we go. Just a tad. So of course our order of set S here is going to be 9 rows times 9 columns times 9 possible digits per cell, 9 to the third. Now the question is how do we use the exact cover constraints to restrict the choices that are reasonable to make from S in our exact cover problem to choices that will represent an actual solution of the puzzle. And the answer is we put our constraints in X. Specifically, for every way that choices in the puzzle can conflict, we put an element of X, we create an element of X that contains all of the conflicting choices. So an example of this, one type of constraint we'll have is the cell constraint, which is the cell can only contain one digit. And so there will be a constraint for each cell, row 1, cell 1, that just is contained within all of the elements of S that pertain to that cell. And because our exact cover has to choose an element of S that contains X, that means we have to put a digit in that cell, and we can only choose one element from S, which means we can only put one digit in the cell. And so that's how we're enforcing the Sudoku constraints. And a similar thing is possible with row and column constraints. So, for example, we can make this the row 1 constraint. And this is actually a per digit constraint, right? So for each digit in each row, you can only choose like one cell to have that digit. So for row 1 and the digit 1, we could choose it to be in column 1, or we could choose it to be in column 2, but we could only choose one of them. I don't think I chose a convenient choice of columns to show a column constraint, but it's very similar to the row constraint. We just, instead of changing the column, you'd have a column and a digit and change the row for each S that contains that particular element of X. And I mentioned earlier that the night move constraint is also an exact hitting constraint. And so an example of that would be, I'm gonna have to bring up the board, or else I'm gonna screw this up. If we imagine, say, this cell, let's call this row 1, column 1, just easy numbering. And this cell right here cannot contain the same digit. Which means that we can only choose one of these cells to contain a particular digit. And so we will have, say, if I go back to constraint, so this is row 1, column 1, and row 2, column 3. So let me write that down. We have row 1, column 1, and row 2, column 3. And so we couldn't choose, for example, row 1, column 1, digit 1, and row 2, column 3, digit 2 together. So let's call this, like, I don't know, night 1 constraint or something. And we have row 1, column 1, digit 1 here. And I will have to write this in down here. We have row 2, column 3, digit 2. Like so. Or sorry, this shouldn't be digit 2, digit 1. Oops. Not mixing and matching digits here. Digit 1. Let me fix that over here too. Where did that? What? Okay. My option to delete it disappeared. I was like, what? Okay. So we have that. However, we of course don't need to put the digit 1 in either of them. And so this particular constraint on digit 1 will also be covered by putting any other digit in either of the cells. The trick here is that we could potentially get a double cover if neither of the cells is 1. And so this is sort of hinting at how we'll handle the arithmetic constraint as well. But we need essentially we need sort of derived choices that represent the idea of putting 1 in one of the cells or none of the cells. And lining the trick with that is lining it up with all of the other traditional choice options. But I'll think a little bit more deeply about the best way to represent that when we're actually in code and can just try stuff and see if it breaks or not. Otherwise, I will spend too much time staring at this and trying to figure out exactly how this is going to work right now. So this is the exact cover and the exact hitting problem. When it's formulated in terms of the original formulation, up here, it's called exact cover. When you're using the exact cover to represent this idea of making choices under constraints, it's called exact hitting, because you have to make one choice that pertains to each constraint. You have to hit the constraints exactly. But they're the same problem. As we've seen, I've just formulated Sudoku in a exact cover problem, and because of the type of original problem that it came from, it's called an exact hitting problem, but the problems are actually solved the same way. So, you wanted a code stream. Here comes the code. Over to PyCharm. Yeah, so where to start with this? I'm going to... I don't have good intuition for the exact cover problem, if I'm being completely honest, in terms of like thinking about the parts. And that's one of the reasons, other than I just like math and rigor, of doing all of this drawing in math in Excalidraw, is that I can copy this work and just name things X and S and S star, and it's not pretty, but it does work, and that is good enough for me. So let's start by I guess just generating S, the sort of like default set of choices, right? So how do we want to do this? Yeah, I think we're going to start with generating S. And I'm just going to start with the basic Sudoku, right? So let's solve, I guess. I don't know. Doesn't matter. So we're going to generate basically just this, which is like 3 loops, but we need some elements. Yeah, I guess the important thing here is that we can index them in this like row column digit format, and get, because we're eventually going to want to turn it into a matrix like this, right? So get an integer index, like a row index. I'm actually going to make these columns. I'm going to pull a fast one, but an index. And the output of our algorithm is just going to be a bunch of indices from S. So we want to be able to return that to sort of meaningful inputs that we can then input into the puzzle. So that shouldn't be too hard. I guess we'll just make a pair of functions for that. How do we want to represent this though? Okay, I'm getting ahead of myself. I was already thinking like choice classes and stuff, but that's a little too far. Man, naming. I'm great at this. Index from choice. We're going row, column, digit. Return. We'll just use a normal like linear encoding here. So we'll do 81 times row plus 9 times column plus digit. Okay. And then we have a choice from index I, and we will return, let's see, the row is going to be it's okay, let me think about it the other way. The digit is going to be I modulo 9, and then I guess we have I divided by 9 is going to get 9 times row plus column. So we'll just make this modulo 9 again to get the column, and then I divided by 81 is, what is, oh, we're done in parentheses. I guess these sub-expressions don't need parentheses. And these sub-expressions also don't need parentheses. Wait, oh, there doesn't need to be any parentheses here because fuck Python syntax. Okay. Fair enough. Is it actually going to complain to me if I put parentheses here? Because there should be parentheses here. Okay. Okay. So that was easy enough. So now we can sort of turn choices into indices. Yeah, good luck. You missed the explanation part. I'm sorry. Hopefully this makes a little bit of sense as I go along, or it'll just be magic. We'll see. Definitely one of these things you might have watch a few times. I will have this up on YouTube later. Apparently making a YouTube channel with an email on your own domain is non-trivial and cannot be done the same day as a stream, let alone hours before. Okay. So now we need to generate constraints, and constraints will just be lists of choices that conflict on the constraint. So we could do let's generate the cell constraints first. So cell constraint will give a row and column. And we'll go ahead and do a list comprehension here. So we'll have the choice that corresponds to that row, column, and picking a digit for digit in range. How is this going to work? 110, I think is correct. Yeah. Okay, so that will generate a list with all of the choices that conflict for a particular cell, so you can't try to put more than one digit in the same cell. We have a row constraint, so we'll choose row, and the row constraint actually involves the digit in consideration as well. And this is just going to, there's a lot of symmetry here, as you can see. Column constraint, I can actually just do this fast now because of the symmetry. And index from choice, row, column, digit for row in range 110. I'm gonna regret this one base. Okay, it made sense for the digit. I'm I'm gonna not do it for the row and column, this one based indexing, because it's gonna get messy very quickly. Okay. So this for a given row and column puts all of the choices corresponding to the digits in a list. They conflict with each other because you can't place more than one digit in the same cell. You have these row constraints where for a particular row and digit, it makes putting that digit in each of the columns conflicting, because for each row you have to choose which column a digit is in. You can't put in multiple columns. And similar thing for columns and rows here. Now we can generate all the constraints. So we could define generate constraints, I guess. And we'll just make a cell constraint for each row and column, a row constraint for each row and digit, and a column constraint for each column and digit. So we'll have constraints, make it an empty list. And then we'll do for or let's make this more easier to read. R in range 9 for C in range 9. So this is going to be row and column. We'll add a dot append. We'll add a cell constraint for each row and column. And we're already going over the rows, so we might as well take the time to go over the digits as well and put in the column constraints. Constraints.append cell constraint. This is row and digit, or this is not a cell constraint. That's why I'm confusing myself. This will be a column row constraint. It's a row constraint, everybody. Just trust that I wrote the rest of the code correctly. Okay. And then we will then go over the columns again. Yes, I was going to try to be clever about it, but we'll just do it here. Easy stuff that works. And then go over the digits and can append the column constraints. Okay. So now we have a way to generate a list of all the constraints that are in a standard Sudoku puzzle. We'll, of course, have to go back and deal with the Knight's constraint, and then the arithmetic constraint is going to be its own amount of fun. Okay, so we have a list of constraints. Basically, I can pull up my list X, and each element in the list X or set X will contain the choices from the set S. So basically what I have here is I have the converse of this relation. I have the relation from X to S in a sort of like perusable list format. Yes. Okay. How this is going to look when we start making the paradigm a little bit more complicated is beginning to percolate in my mind. Um, but we'll save that for a little bit later. No reason to jump ahead of ourselves. So now we want to constraint. We want to create this instance table. This one right here. And so a question we might have is what size of it, first of all. And it will be the number of choices that we have, which is 9 times 9. And I'm going to make those. I said I was going to make them columns. I don't know if that's actually the best idea. I probably shouldn't think in terms of row and columns, because this is how I get myself confused and asking whether the first subscript or the second subset is rows and subscript is rows and columns. Doesn't matter. We are going to, and this is the part where I have a little bit of an existential crisis, the fact that there's still, in 2022, no good way to just generate an empty array of a certain size in Python, because that's not how Python does things. So we want an array that's, I guess we'll generate constraints, right? So we'll have constraints equals generate constraints. Amazing. I did a JavaScript right there, tried to put a semicolon. So it'll be 9 by 9 by 9 by len constraints, right? Does that work the way I want it to? Sure. Yes. So we'll make the instance table for our relation, and we will make it. Can I just? Is there a way in Python to just generate a list of? Yeah, I could do. If I do. Len constraints times list containing 0. However, I think this needs to be let's just try this. I know there's weird rules with like aliasing in list comprehensions, but this might just work. 9, and there's an exponent operator in Python, so I'll just use it. So my question here is, first of all, what happens if I set relation 0, 0? And then what happens if I set relation 1 to just be like empty? Print, what does relation 0 look like? There's going to be a lot of constraints in there. That's fine, whatever. We'll just see what happens. What does relation 1 look like? What does relation 2 look like? So let's see what happens. Oops. Oh, whoops. I need something in here, in range. There we go. Oh, I had a name in here. Because it was used for the hello world function. Okay, so it seems that there's no aliasing in our array anywhere. That's good. Okay, just had to make sure. Okay, so now we want to fill the relation, and we'll do that by going through the constraints. So for constraint in constraints, for choice in, and these will already be indices, choice, I guess I should specify that, for index in constraint. Let's see, this needs to be an enumeration of constraints, doesn't it? So for in I don't remember what the output of enumerate is, so I'm just not going to guess. Enumerate constraints. Okay, it's index and then the actual constraint first. Okay. Sure, whatever. Names. And then we will, yeah, this should work. So then for C in constraint, relation, C I equals 1. There we go. So this should generate an incidence table. It, of course not. There's an off by 1 somewhere. There has to be, right? Okay, so first of all, is it a C problem or an I problem? It is a C problem. Interesting. Oh, this is because these all need to be, okay, fine. Because of the way that I'm encoding indices from choices, these all need to be 0 base. I should have known that was going to be a problem. That's my fault. Why is it still a problem? This should no longer be a problem. Issue. If I catch the index error, it'll tell me what the index was. Why does Python do this to you? Like, I guess I could just print C and see what the index that failed was. 729? That sounds well within range, is it not? Is it just not? Let me pull out a calculator. 9 times 9 times 9. Oh, it's exactly out of range. 729. Amazing. That shouldn't be an option anymore, though, because we should have... Oh, it's because I... God damn it. Because I'm getting invalid shit down here. Okay. That should be fine. Okay. 728. That's what we expect the last one to be. Okay. So now we have this instance matrix with... cool, yes. With ones where our choices and constraints are related and zeros elsewhere. And now we can do the algorithm. So we will call this algo x, because that's what it's called, because you thought I was bad at names. It turns out that Knuth is worse. So we'll perform algo x on the relation. And the first thing we're going to do is helper. because I don't feel like making actual... What is the issue here? Oh, unexpected argument, because this should be a different function. Because I don't feel like it making an actual tree structure, and the depth, recursion depth, if we do this recursively, should be only like 81-ish. So should be fine to just do it recursively. It will be much easier to think about that way. What am I doing here? Okay, pass. Oh, this should be relation ACK. Okay. So we're going to use this this ACK to accumulate our choices of sets for our cover so far. Okay. I'm envisioning a problem here, but I will solve it later. If it actually ends up being a problem, I might just decide that I don't care. Okay, so now that we have this instance matrix, so the first thing we're going to do is we're going to look at whatever corresponds to what previously was columns, which should, if you consider the first subscript rows, it should still be columns. And we're going to find the one with the minimum count. I also want to include some things. Let's do one. This is just some sort of like interesting informational stuff that will allow us to print some pretty output, or not pretty output because I don't make my output pretty, but useful output. I'll include a depth counter as well. So our implementation here is we're going to first, I guess, our relation could be empty because we could have solved it, right? So if a relation is empty, equals 0, then the cover that we're given is just correct. Now, okay, assuming our relation is not empty, we might ask, is there any of these sort of columns where it's already deducible? What is like the easiest constraint to satisfy? So we're going to want to keep I guess let's just guess the first one for now. So easiest constraint is equal to, I'm just going to keep the index of it, index 0. And easiest constraint, let's see, difficulty of this constraint is going to be, do I have infinity? There's got to be. What is the, it was just inf, isn't it? What is the infinity constant in Python? I can't. Oh, I guess I could just initialize this to what the actual difficulty of the first constraint is. So let's get a constraint difficulty. So constraint, I'm being perhaps more free-flowing with the function definitions than I normally would be, but smaller functions are easier to understand anyway, so it's probably good. So constraint difficulty. So we have relation, and we have constraint index that we're interested in. And what is the difficulty of it? And we're going to define the difficulty as the number of ones that are in that particular column. If it's 1, it's very easy. We have only one choice. If it's high, it's harder. We just have to randomly guess. And we're just going to try to solve the easiest constraint every time, because it will hopefully involve minimal backtracking is the hope. So we'll have difficulty equals 0, and then let's see, for R in this case is going to be a relationship element in relation constraint. Yes. Difficulty equals difficulty plus R. I can just sum. Difficulty equals sum of relation constraint. Man. Wow. Peak functional programming right here. Okay. So difficulty is equal to constraint difficulty on a relation and 0. Then we're going to do for constraint in range. We'll start at 1 and go to 9 to the third. That's the number of constraints, right? No, it's not. The number of constraints is the length of our relationship. One when relation. Constraint. Actually, let's not do this. If constraint difficulty of the relation. This I could probably minimize somehow. There's definitely a functional programming way to do this that it's almost 2 a.m. Give me a break. Constraint difficulty on a relation, and then on the constraint is less than the difficulty we found. The easiest constraint is the current constraint, and its difficulty is equal to the constraint difficulty. Okay. So that's just finding the minimum difficulty constraint. Amazing. Oh, it doesn't return anything because I'm dumb. Return. Okay. So we have the easiest constraint. Now, an interesting thing to print out would be print depth plus the depth, right? Just print the depth, and then the difficulty of the depth as well would be good to print. This way we can see how hard what we'll get from this once we have a solution is we'll get basically some sort of measure of the difficulty of solving the problem over time. If you have a series of depths in the solution that has high difficulties, then there was a lot of choices and a lot of risk of backtracking at that particular depth. If you have one choice at that particular depth, then it's very easy. You actually have only one choice you can make. You can make a deduction at that step. And importantly, and this should be, let's make the end nothing just in case. Importantly, if the easiest difficulty is 0, equals 0, then we'll print a new line and return none. If the difficulty is 0, that means there's actually no set that satisfies that constraint. And so it becomes much harder. It becomes impossible. And so there's no solution. Shouldn't happen in any actual puzzle, but it's a possibility that could come up. So now we have the easiest constraint. If it's one that's, or if its difficulty is one that's very cool, but don't really care. In the sense that I'm not going to make a point of treating that case separately because it's just a degenerate case of trying to guess all of them. It's just you're only guessing one thing. So, I guess the thing to do then would be to construct a list of the constraints that we, or choices that we might consider making. So we have for, so we want to go back into that constraint and yeah, okay, so we want to go back into that constraint and find what choices are involved. So choices equals I'm thinking here because if we had the actual constraints table, this would be much simpler, but I'm not going to pass that in because it's going to make things more complicated. So we need to reconstruct it from the relation. So choices, and then for I guess we want to enumerate the row in the relation relating to that constraint, and then I guess yeah, for I are in enumerate relation easiest constraint. Okay, so we're enumerating the elements in relation to the easiest constraint, and then I guess if r equals 1, this is a choice we're interested in. So choices dot append I. Okay, so these are the possible choices that we can make to satisfy the easiest constraint. Now we're just going to try making them. So for C in choices, we're going to have some sort of function that is like make choice that gives us this update step that we did, where we did all this row crossing, column crossing out, does that on the relation for us. Which I can probably, if I'm very clever about it. Don't know if I should be this clever about it, but if I'm clever. Oh, sorry. if I'm clever about it, I should be able to make a list comprehension for that or something. But we'll worry about that when we get there. I will just define this so that we're not being yelled at. Define. Make choice is what I called it. Make choice on the relation and choice. Pass. So to be clear, I guess I should return something. Return empty relation. So to be clear, the intent of this function, and I will go back and actually write it, is that it reduces the relation to the things that we have to consider in the next step of the algorithm, given the choice that we just made. Then we're going to have like new ACK is equal to this, a copy of the previous ACK, and then append C, I guess. And the depth is just going to increase, right? So we're going to get the result of using this new relation, this new accumulator, increased depth, and then if result is none, continue. Actually, is not none. We'll return a result because it will be a successful solution. Otherwise, we'll just keep going. And if we tried all of the choices and failed to find a solution using any of the choices, then there was no solution. That should just work. Okay, so now this choice making algorithm. So I guess what we should do is we should. So we've made a choice, say like a choice like 3. That'll tell us what columns we want to get rid of. And then the columns will additionally tell us which rows we want to get rid of. And then we'll go through and get rid of all of them all at once. Okay. So the columns we want to get rid of precisely correspond to the indices of where the ones are for the constraint that or the choice that we chose. So these are our constraints, and these are our choices. So we take our choice where there's ones; those represent constraints that we want to remove because they've been satisfied. So we'll have let's see, constraints, I guess, to remove for our relation is constraint followed by no, it's not. It's choice Okay, that's confusing. It's choice. Now I have to make sure my relation to access has been correct. The first subscript of relation is a choice, and the second is a constraint. First is a choice, and the second is a constraint. Okay. So is that consistent with what we've been doing so far? No. No is what I'm getting. Yes. So we want this is not over constraints. This is over choices in the relation. But this going over constraints is kind of important, so I might just make the relation constraint valued. Like, why not? Or like make the first subscript constraints. So we can just do that. Each constraint. And then wait. No, we do want it to be a choice. We want to go through. I knew this part was going to come. Okay. Get this straight. So we have the relation with first subscript choices, second subscript constraint. I guess the truth of the matter is we want to be able to access a relation in both ways, and that's not trivial. Because this, we want to know about the difficulties of the constraints. This will be constraint. Yeah, see, I summed a choice here. But we actually want to sum over relation I constraint for I in range len relation. Now we're thinking with list comprehensions. Okay. Cool. Okay. So this is, we're putting choices and then constraints. We are reading choices and then constraints. Here we are this is the other concerning part right here, because this should be some sort of constraint access. But I think this might be easier, because if I do for I in range len relation, it gives us all of the choices, and then I can just ask if relation for that choice on the easiest constraint is 1. There we go. Okay. So fix that little mistake of mine. Back to constraints that this choice will affect. So for I in range len relation choice, I guess, doesn't really matter. Could put 0 there. If that that particular constraint is satisfied by that choice, we will append that constraint to our constraints list. So that's the constraints, the columns that we want to delete. So say we chose 3, we go through, we find the ones, and those are the columns we want to delete. Now we want to find the rows we want to delete, which is going to be the union of the union of the union of like where the rows where all of the ones are within those columns. So for that we can do something like as we want, like for C in constraints, we want to enumerate everything in a constraint. So for I in range in relation, so just considering choices. We have Sudoku indeed. Very, very slowly. Yes, I knew we were gonna run into this part where every line feels like a drag because nothing is very intuitive about this representation of Sudoku. But it's just a trust the math and it works kind of thing. We've done the math. This should work. Okay. So we'll make a list of choices we want to delete as well. And then, yeah, I guess we can just, so because we're going over 2 loops here, we're going to put choices in. So we're going to put values of I, but we could run into multiple ones. So we have if I not in choices and relation for that choice on that constraint. We have 2 things this way. Yes, please sleep. It's late here as well. This will be up on YouTube at some point. If you follow me on Twitter, I will post when I have it up on YouTube, so you can definitely... You're not missing anything. Please go and sleep. I also shouldn't be using this like... that's unfortunate. Yeah, I mean, you can follow me here. I do not have the YouTube yet, unfortunately. What you can do is I'll make sure to put it in my cards or something, and you can come back to the channel later and find it. Then we will append this choice. See ya. Have a good sleep. Okay. Did I do that anywhere else? Also, God, these semicolons. It's like habit from both C, but also like JavaScript, where I actually want those semicolons. I guess in principle I should want them in Python as well, but yeah. Okay. I'm just checking that I haven't like read an element from a relation and tried to treat it as Boolean when it's actually an integer. I don't think that's a problem in Python, but I'm not about to find out the hard way. Okay. So that should be good. So now we have the choices and the constraints that we want to remove from the relation. So now we go through all of the choices, skipping the ones we want to remove, and then taking those constraints and adding them stripped down to a new relation. So this is going to be our new relation. Yeah, that should work. So we're going to do for I in range length of the relation. So going over the choices. If I in choices continue. If not, we're going to append strip choice. Strip choice constraints. So strip choice. This will be relation I constraints. Okay. And this will be very simple. We'll just take a choice, the constraints we want to strip from it, and then we'll do a similar loop for I in range and choice. If I in constraints continue. And it's very important that I'm making new lists here every time. That's kind of one of the reasons why I'm unrolling this into this sort of lengthy like loops that I am, when I could do probably some clever thing with list comprehensions or something, is just to make it clear that there's no aliasing here, which is important when writing recursive algorithms in Python. So we have that append choice I. What is going on here? Unexpected argument. Oh, there's extra parenthesis there. That's okay. Okay, so that will do that, and then if we return our new relation, that should be fine. So in principle, assuming that I've made no mistakes, which is this should be algo x impl. Oops. Assuming that I've made no mistakes, which is always quite the assumption, this should generate a solution to a Sudoku puzzle. And in particular, it will generate a solution to an empty Sudoku puzzle. So I guess we'll just print the output and see what happens. It's not going to be readable. We'll worry about that later. But let's just make sure it actually gets a result, and two, that the result is seemingly reasonable. Nope, of course, index out of range problem somewhere. Wait, how is that? What? The constraint must be... The constraint itself must be out of range. Because, yeah, I is just going over the length of the relation, so it's going to be fine. So if I print constraint here... 243. The constraint will be from the constraint difficulty. Where is this being called? This is being called all the way down here. Constraint difficulty. Relation 0. 0 will always be in range. The constraint is one in length relation when it should be, in fact, in range length relation. 1 length relation 0. I really confused myself by making the first subscript. Choices and not constraints, but I feel like it would have just been the other way around. Confusing the other way. Oh, of course. Python doesn't have types, still does this shit to you. Classic. Oh, I should remove the print up here too. It's just where is it? Up here. It's just printing a bunch of nonsense. Okay, and then okay. I am in stack traces are hard to read mode. Yes, clearly, which is strange because I feel fine. I do not feel tired, but clearly I'm running out of steam for this today. So after I get this working with basic Sudoku, I will probably leave the adjustments for additional constraints for next week. Make choice. So append I. Choice is an integer. That sounds like something dumb that I would do. Like forget an S. That is in fact something dumb that I would do. Non-type object is not subscriptable. What have I done? What have I done? Alright, so let me just print relation. I assume it is literally none. Oh no, it's a... How did that happen? It is an array of lots of ones. I realized that I left the ending off here in anticipation of potentially writing some other stuff, but I haven't done that yet, so I'm gonna go ahead and drop that. A relation became a bunch of none. Why? Struggling. Buffer is struggling. So this would have come from... Oh, interesting. I'm curious for a second. If I remove this print the relationship. But this is very soon. It gets into one level of recursion. So that's what comes out of our make choice function. So we're gonna print C just to see what choice is made right before. So 0 is the choice that's made. Why don't we do some classical debugging, see what happens. Okay. Let us continue like through the loop. Continue. So it shows 0, 9, 1, 62. Right. And so this... Actually, that's not enough. that's already a problem. There should be... Oh. I am dumb. Okay, that's fine. That'll be an easy fix later. I was gonna say there should be 4 constraints here. Like putting a number in a cell satisfies at least 4, or when the grid is empty, it satisfies 4 constraints. It satisfies the constraint that there only be one number in the cell, that number appear in that row, in that column, and in that box. And there's only 3, but it's because I didn't make the box constraints because I forgot. That's okay. So I'll go back and add those constraints later. I will get it done this stream, even if it means I go for another hour, but so that we can at least solve a Sudoku puzzle. Okay. So that's why that number seems wrong. But it is in fact not. So we'll now continue. And choices. So these first 9 choices are putting anything in the same cell. Then we have these choices by 9s, which are going to be putting that digit in anywhere else in that row, I believe. And then we have the ones by 81s, which are going to be putting that a strip choice must return none because I screwed something up. Probably because it doesn't return anything. Yep, that'd be it. Okay. Real mystery, that one there. Okay. Alright, let's run it. Let's see what happens. Okay, so we get to depth 81. And it prints none. So the final result ends up being none. Which is good. So this, what we're having it do right now is we're just having it fill in a Sudoku grid. It's ignoring the box rule, and it's just picking numbers. And this sort of thing where at first you could put basically anything in, and so it is hard in the sense that it's hard to know what you should put in. But it's not actually hard in the sense that if you just try, you will probably do it correctly. And as we can see, I don't think it backtracks ever. I think it might just figure it out. Yeah. Because, I mean, it's simple Sudoku constraints is a computer, and I've given it the very simple task of just filling a Sudoku grid with any reasonable combination of numbers. So that's perhaps not too surprising. Kind of interesting. I expected to have to backtrack at least a couple of steps, but it seems that our easiest constraint thing is working good. Now the question is where are all those prints coming from? So that's the numbers. Yeah, I guess this will just do it, right? 81. Turn none. So if we get here, let me, print. That's actually really cool that it. I wanna try that again. Yeah, see, auto corrected so because it knows what I'm doing. Okay. Sorry, I just had to gawk at IME magic again. Hit fresh again. So let's see what the relation is at this step. That is interesting. It does not print anything. So it should hit. My expectation is that it would hit one of these returns. One of the two. Let's see which one it is. Surely. Yeah, it hits this one. Okay. So it returns this great list. Result is well, I don't know about great list. Actually, I can tell it's not a great list because it is. Uh-oh. I should have expected this to happen. I did not quite anticipate it working that way, but that's fine. We'll go back and fix that. The problem here is this is the accumulation of choices, right? And it so why is it 80? It should be 81. Okay. It's choosing the same thing multiple times because it's choosing each time it's choosing the index based off of its relation, which is not unlikely to be the index in the original relation. We need the indices in the original relation. It'll be interesting to see what the best way of translating that back is. But I'll figure that out after I figure out why this isn't. If I just go next. Result is. Oh, it is a list with 81. Oh, okay. I was looking at ACK, which is okay. Yeah. Return result. Okay, it does. Okay, what is the issue here then? It feels like it's going to keep going up the call stack, and result isn't getting smaller each time. Okay, that's not the problem. Oh, is the problem that result ends up referring to a list that I allocated right here, so it falls out of the scope and becomes none? God, Python, I hate it. I hate it. That can't be it though. That's not how Python works. Because you can just like return lists and stuff. So that can't be how that works. Surely. Okay. There's probably a faster way than clicking through this. There's probably like a break only in this stack frame or whatever, but like result stays the same. So it should be returned from the last stack frame. Oh. It's because I don't return it from AlgoX. Wow. Imagine that. I haven't even spent all that much time programming in Rust, and I already write my code like it's Rust code. Great. See, this is what types are for. If I had types, it would tell me that I'm not returning anything, and it would yell at me for that. But no. Instead, this is an acceptable thing to happen in Python. Okay. So that's cool. I guess not really. Because it's completely unreadable. One, because it's a bunch of numbers. But two, because the basis of the numbers also changes. So I'm hating that the solution to this is probably to go through and make relation a dictionary from integers to integers, or like nested dictionaries. Yeah, I mean, I guess that's going to be the thing to do, right? How does it even work? Dictionary comprehensions are a thing in Python, I'm pretty sure. Let me pull up my reference device. Dictionary comprehension Python. What does a dictionary? I guess it's got to just be like key colon value for in. Yeah, it is. Okay. It just looks really weird to me because I've never seen many dictionary comprehensions, but it should be fine. So a relation is going to be a dictionary on choices from I to a dictionary on length constraints j to 0 for j in range len. What was it originally here? Len constraints. Okay. J to 0 for j in range. Whoops. Constraints. Okay. So all I'm doing here is this is gonna run into problems real quick. Updating this to be this is gonna become a problem real quick. Updating this to be a dictionary everywhere. But the idea here is that I'm making the relation a dictionary from integers to integers instead of lists, so that I can remove keys without shifting all of the other keys. That's the idea. So now I just need to go through and make sure all of my computations on relations are correct. So we're going to start with constraint difficulty. Yeah, even just thinking about this as a dictionary is really tough. Key value. So if I do like key value in like relation dot items, I think is what I want. And a value will be this, so I can just do value constraint like so. Think that should be fine? Okay. So that's our constraint. Difficulties. This makes stripping choices a lot easier though, because it's just deleting items from a dictionary. But it does need to be a new dictionary. So we can actually use a comprehension key value for key value in choice.items. And then I can actually just for I in constraints delete IC or CI, I think is correct. Return C, okay. So like for key value in I should not have, this is relation choice, okay. So make choice. So for key value in relation choice items, if value equals 1, constraints.append key. For C in constraints, for I in range relation, so we actually want key value in relation.items. If key not in choices and relation key C is equal to 1, choices.append key. Excellent. Okay. And then relation I in range relation. So we'll do a similar thing as we'll do, so we can just make the comprehension. Key value for key value in relation.items. So we'll make the value should be strip choice value constraints constraints for key value in relation.items if I not in choices, or sorry, key not in choices. There we go. I'm guessing that one comprehension would also work up here somewhere. That like one line comprehension would also work up here. If I not in constraints, or key not in constraints. Oops. Key not in constraints. Cool. Excellent. Which is, as I predicted, this whole relation can be written as one nested comprehension. I'm not going to do that because that just makes code unreadable for no reason. But my intuition that there was a sufficiently functional way to do this was in fact true. Okay. And now I guess we just look at this impl to make sure I didn't screw anything up, which I definitely did. Well, not screw up. I didn't plan for this to use a dictionary in the first place, so. Constraint. For constraint value in just in relation 0.items relation 0.items. Yeah, I guess I'm just like trying to go over the constraints that remain, so it doesn't actually matter. Then we're going for choice value in relation.items if value choice. I want to say that's good. Of course it's not. Key error 0. Print relation. This is probably going to come out to something rather large. Is in fact going to print these potentially large things multiple times. I don't know why I expected any different. Key error 0, and that 0 is no longer an option in most of these. Yes. Actually, it shouldn't be an option in any of these. So the question is how did the constraint difficulty... Oh, I think I have it literally... Yes, this one right here. Easiest constraint is equal to item is equal to relation.items 0, and we'll just make this item we want like item.values relation.values.keys 0. Easiest constraint. Oh. Awkward. Probably because we want to index into it. Okay. There we go. Changing to a dictionary. I should have figured a dictionary would have been the way to do this right from the beginning. But lesson learned. Dict values object is not subscriptable. Of course. Of course Python would do that to me. Why is it not? Is a keys object at least? Come on. If I can't do relation subscript relation dot keys 0, I'm gonna be very unimpressed. Please, Python. Why do you do this to me? Only Python would be a language dumb enough to decide to make the decision that something being iterable and it being subscriptable is not the same. And it's not due to any reasonable reason, like having iterators being robust to changes of the underlying object during a loop, because that is not the case in Python. So yeah. What is the easiest way to do this? This is really cursed, but I can't think of a better way to do this. For I and relation dot keys for j in relation I dot keys, easiest constraint equals relation I j break. The fact that I even have to write that makes me very sad, but easiest constraint might be fine, whatever. Equals -1 could be valid though. Let's just make it none, just in case something terrible happens. Key error 1. That's not a key error. What? So you're telling me only some of these items do not contain 1 as a key either. I probably shouldn't be surprised. Okay. For key value in relation dot items, print value. Let's see, if value dot if 1 not in value, print value, something like that. So there seems to be a bunch of options not containing 1, 9, with 1 and 9 missing, but a ton of other stuff there. That's kind of strange. Let me just look at like strip choice and stuff and make sure that they are returning reasonable things. I'm concerned that we might have some amount of aliasing going on, but we'll see. 171. What do those numbers correspond to? So the constraint numbering is, I guess it's sort of arbitrary, right? It's like whatever order they were added in. So the real question is how do we come back here asking to like remove something? That isn't there, because this seems to be working fine, which I would hope so, because it's a very simple comprehension. Not that I haven't fucked those up before, but I would like to think it does exactly what I think it does when I read it. But that's sort of the thing, right? We don't like to think that. Oh, it's a problem in constraint difficulty. Oh yeah, it always was. Okay. Oh, we don't want it to be, okay, this is reading a value. We want it to just be J. Okay. This is a similar problem. We need to know what the first key is. So we'll do for k in relation dot keys. We just need a valid key. And then we can break immediately afterwards. Okay, let me remove this because it'll go crazy. 0, 10, 20, 30, 40, 50, 60, 70, 80, 82, 99, 10. This looks like it might be workable. Shall we pretty print it and see if it solves a not particularly, we aren't quite to Sudoku solving yet, but if it fills a grid in a manner that meets our expectations, which, to reiterate, is we have row constraints, column constraints, and cell constraints. So we're ignoring the box constraints that normally come with Sudoku for now. And then we'll add those in afterwards. And we have no already input numbers, so the grid is empty. And that's why it doesn't struggle very much at all with coming up with a solution, because we just ask for any solution whatsoever. And so it just comes with a trivial one where this looks like it's... interestingly, it looks like it decides to put one like down the diagonal or something before doing other stuff. Let's go ahead and pretty print this. So we're going to have the result equals n. If result is none, print impossible. Else we're going to have, we'll just do the output be another list for I in result. So we want choice from index. So choice equals choice from index I. But we want the output to have a nice string. So we'll do row plus string choice 0, which is the row. We'll add 1 so that it's counts starts from 1. This will be the column. C and then plus. I used D when I was writing, but I'll use hash because I think it'll read a little bit better, and then plus 1. Okay. Then we'll print the output. So this should give us yes. Okay, so it is doing the sort of reasonable thing that you might expect. I might go across the row, but it's going down the column first. No, it is going down the row. It's going down the row and just incrementing going up, just going 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it has done the clever thing of swapping 1 and 2 in the obviously you can't do this with the box constraint, but with just the rows and column constraint you can simply swap 1 and 2 and keep going ascending. And then it's decided to start at 3, so it's just choosing to bring one of the numbers up to the front, and I assume it does this all the way down into the bottom row. So this will create, not including the box constraint, a valid Sudoku solution. So now we need two things. We need to introduce the box constraints, and then we need to introduce some numbers, ability to put numbers, which is actually that'll be very simple. Yeah, and then we will obviously won't solve the original Sudoku puzzle that we wanted to go after, because that has some more advanced constraints that we will take a little bit of thinking to break down. And frankly, I probably should prepare a little bit more for the next stream and explaining how we're going to do those constraints instead of doing it off the cuff anyways. So that'll be a good stopping point, is getting regular Sudoku solver working, and we'll get it going on the advanced puzzle. So first, the box constraints. Also has import math that we don't need. Cool. We have comments that we don't need. Okay. So first, putting in the box constraints. That shouldn't be hard. It'll be a little bit trickier than the other constraints. So box constraint. So I'm going to give a row column. This is just going to be the like row column of the do we want to do it as the top left of the box? Nah, it's fine. We'll do it as the row column of the box within the like 3x3 grid of boxes, right? Actually, there's a reason why I should say yes, we do want to do the starting row column. Actually, fuck it. We're going to need that later, so we're going to do that. We will go ahead and have this row column be the top left corner of the box. And then we do return index from I don't think we can do this as a cool list comprehension. Let's just do it the easy way. Constraint equals that, and then for I in range 3, for j in range 3, constraint dot append index from choice row plus I, column plus j. Oh, there's a box constraint for every digit, isn't there? That's excellent. Okay. And then digit. Okay. Now when we go into generate the constraints, this is where we'll do for I in range 3. So this is not going to be the for j in range 3. This is not going to be the top left coordinate of the boxes. This is going to be the coordinate of the box in the like 3x3 grid of boxes, and we'll expand that out in the coordinate. Top left coordinates for the box. And then for each digit, constraints dot append column constraint. Or sorry, it should be box constraint. I times 3, j times 3, and a digit. Okay. So now, if we do that, none type is not iterable. Let me guess, I didn't return. Man, how did I guess? Cool. So now, as you can see, it chooses. This is a lot more interesting. So it puts the 1 in the top left, and then it tries to put a 1 in the next box over. And it can't do it in row 1, so it goes to row 2. And the first place it can put it in that fits in that box is the 4th column. And then it does the same thing with the next box in the top right. Can't be on the 1st or 2nd row, so it goes to the 3rd row. The 1st column in there is the 7th column. Okay, so now it respects the box constraints, and if we put all of these entries into a Sudoku grid, it should be a valid filling of the Sudoku grid. Now the question is, can we get it to solve an actual Sudoku puzzle now? And the way we would do that is simply by, instead of giving the original full relation, here in the solve, we generate the full relation, and then we just pass it the relation. We would simply make some choices, forcefully make some choices of different numbers before we give it to the algorithm. So let me see if I can't look us up a simple Sudoku solving site of some description. Sudoku Okay. Yeah, it seems seems like we can just go to sudoku.com/evil. Okay. So this is the hardest. This is some Sudoku site. I don't know. First hit on Google. I don't care. I just need a puzzle to solve. This is the most difficulty. So it's probably pretty challenging for a human. But let's see how the machine fares. So all I'm going to do is I'm just going to start. Let me do one of these so that relation is equal to make choice relation, and then if I do choice from index, I don't want that. I want index from choice. If I just do row 1, or it should be row 0, column 0, and the digit is going to be 6. Can I make a helper from this? Just so that we're not reading these like off by 1 things all the time. It's not a huge deal, but it'll just make this a little bit like more user friendly, I guess. So I guess we'll call this hint, because these pre-filled numbers are called hints in Sudoku. Although, I mean, ironically, they're called hints, but a little bit ironic given that most Sudoku puzzles do not have a unique solution without them, so they're not really hints. They're kind of important parts of the puzzle, but that's whatever. Row, column, digit, and then we'll just return index from choice, row -1, column -1, digit -1. Okay. That way I can just write the hints in with a shorter function name, and it will read hint 1, 1, 7. And if I solve this, I'll give some solution. Interestingly, it tries to solve the 7s first, because it would have put a 1 here normally, but it's like, okay, there's a 7 there, let's start putting 7s everywhere else. Cool. So now, this will be a little bit tedious, bear with me, but I'm going to slowly fill in all of these hints. And it doesn't actually matter which direction is rows and, well, I mean, obviously rows and columns, but it doesn't matter that I get it correct as long as I interpret it consistently. This will be column 6 is a 9, and column 7 is a 5. This is the moment of truth. It should be good. Should be good. I don't see why it wouldn't be. What'll be interesting is after this, we should be able to also like make a judgment of how hard this puzzle would have actually been to solve, based off of some of the printouts that it gives. So we'll look at that briefly. So this will be row 2, cell, column 3 is a 6, 7, 8, 9, 5, 6, okay. And the next one over is a 7. That's all for this row. Down from the 6 is a 3. And in the 8th column is an 8. The next row is just 1. 4 the third column, and it is also an 8. Relation. And okay, so this is the 5th row. And the 5th column is a 1. We go 2 cells over, and we get a 9. We have 4 hints in this row. I'm going to be honest, in terms of Sudoku, I've seen this doesn't look that evil, but also I haven't tried it, so we'll see what the computer thinks of it. 6, so the first is a 4, and then next is a 2, and then 2 over is a 3, and the 8th is a 5. Another in, are these actually the same position? It is. Same positions in the row, different numbers, different column, or different numbers, different, yeah, row. So it's a different row. Okay, and then we have relation equals, make choice relation, and this is 8th row, 1st column, 6. And then 2 more. 9th row is the 6th digit is a 3, and the 9th is a 4. So first, fingers crossed actually gives it okay. It came up with a solution very quickly. Okay, yeah, so it did have to do some backtracking. Okay. Yeah. I would consider the description of this puzzle as evil rather accurate. Right, so it gets down here. So at its 16th choice, it has a 50-50 to make. It makes another 50-50. And then it has to go a good like 20 choices, fill in 20 numbers before it realizes it's wrong. And it goes back up and chooses again here. And immediately runs into another 50-50 choice. That's brutal. This would be like... And it's only like, it's mostly deduction. There's just a few 50-50 choices. It'd be kind of interesting to like follow along with this and see if it's like easier as a human observer to like foresee the issue that'll happen with these choices. That's quite possible. The other thing is like when it's going through these like sort of one like deduction constraint solutions, it doesn't do them in any particular order other than the order they are in the relation. And so it could fill out a bunch of stuff that isn't like particularly relevant to determining if the choice at the 50-50 was correct or not. So this is not 100% accurate representation of maybe how difficult this puzzle is to solve, but point is there's multiple points, and at least one point where there was actually 2 nested points where you will have to make a 50-50 choice and deduce that one of them is incorrect. In any case, let us try this solution, shall we? So if this is a dangerous game I'm playing here, just show my desktop real quick. Oh, there we go. That's what I wanted. So if we enter this, then it should be fine. So it found row 5, column 1 to be 3. Oh, does it auto fill it? What the? Oh, no, these are hints. Okay, I was like, what just happened there? The highlighting was confusing. Row 9, column 1 is an 8. Row 8, column 2 is a 3. Cool. Row 8, column 3 is a 4. Row 5, column 3 is a 5. Oops. Hey, that's wrong. What was it previously? 4? Yes. Okay. 5. Cool. Row 5, column 2. I guess it helps that this site has an auto check feature, so anytime you get to the 50-50 guess, you just have to realize it's a 50-50 guess and just pick both of them, and it'll tell you which one's right and which one's wrong. Not quite as fun. Or maybe more fun, considering how painful that search tree looked. I guess the other interesting thing about this is that in the scheme of Sudoku that a computer could try to find a solution for, this one is actually quite easy in that it contains only 50-50 choices and in relatively sparse occurrence. So this is a 6. Row 6, column 3 is a 7. 7 now is just like filling out stuff in a box that I could figure out. Row 6, column 5 is a 9. Okay, that's an interesting direction to go. Go for it. Row 8, column 9 is a 5. It's row 8, column 9 is a 5. Okay, sure. Row 9, column 3 is a 2. Row 1, column 3 is a 1. Row 7, column 3 is a 9. Row 7, column 3 is a 9. I guess, I mean, like, obviously ones like this are, very easy to fill in. But this is a 1. These are all difficulty 1 fills, so even the ones that look like way off had to be the only you had to be able to deduce that had to be there at that time. It's not just like a lucky, well, I guess some of them could be lucky guesses, but in general it's not gonna just be guessing at this point. 9, row 4, 1 is a 1. Row 1, column 4 is a 6. I'm thinking it might have worked. Row 1, column 5 is a 4. I like how I just figured out that whole row. Like, what human solver is just like, yeah, let's do this whole row right now. It'll be fine. Row 1, column 5 is a 3. Oops. What was that? It will not let me undo. That's fine. 1, 2. It was a 4, right? This is a 3. Row 2, column 6 is an 8. Row 2, column 1 is a 2. Row 2, column 2 is a 5. Row 3, column 1 is a 9. Let me guess, you're going to tell me this is a 4 next. Amazing. I'm almost as good as a computer at Sudoku. Row 6, column 6 is a 6. Uh-oh, that bodes well. Row 7, column 6 is a 1. Row 3, column 4. Row 3, column 4 is a 1. Row 4, column 7 is a 2. Row 4, column 4 is a 5. There's never been better content in Twitch. Just someone filling in a Sudoku from an answer guide, pretty much. Row 4, column 5 is a 7. Row 4, column 6 is a 4. Row 4, column 8 is a 6. 4, column 9 is a 3. Row 5, column 6 is a 2. Row 3, column 6 is a 5. Row 3, column 5 is a 2. Row 5, column 4 is an 8. Somehow, I don't believe this is going to screw up at the end. I just got a suspicion that it's going to do okay. Row 3, column 9 is a 6. Row 3, oh, that was right. Okay, column 7 is a 7. Row 5, column 8 is a 4. Row 2, column 7 is a 4. Row 7, column 9 is an 8. Oops. Row 6, column 9 is a 1. Row 2, column 9 is a 9. Row 2, column 8 is a 1. Obviously, this is not difficult for human solve at this point, but I just need to check the work of the computer, make sure I didn't screw something up in the program. Row 7, column 5 is a 6. Row 7, column 7 is a 3. Sorry, I spaced out a little bit. It's like trying to make sense of what I was reading. Oh shit, what was that? 6, there we go. Row 8, column 5 is 8. Row 8, column 6 is a 7. If it screws it up now somehow, I'm going to be very upset. Next over is a 1. It's a 9. Eight, 4 is a 2. 2. Okay. 2, 9, 4 is a 9. 9, 5 is a 5. 5, 6, 7 in that order. Okay. 5, 6, 7. Okay. So it works. What a relief. and it solves Sudoku puzzles that would be patience testing for a human solver quite efficiently. Even dumping all of this output, it solves it in fractions of a second. So that is sort of an interesting point. Is in principle, all Sudoku algorithms are going to be worst case exponential time. And so in principle, just like guessing entries into cells and like doing a search that way would be not particularly slower than this. But in reality, because you can see even in this really hard Sudoku puzzle, most of the entries come from direct deduction, with only a few points of guessing or like multiple possible choices. This algorithm actually ends up saving a lot of time just because it picks the sort of like efficient, easy wins that happen to be all of actual Sudoku puzzles that we challenge ourselves with. Because that's what we expect from a Sudoku puzzle. We want to have fun deducing things, not guessing until we fill the grid with numbers. So that is a Sudoku solver for normal Sudoku done. The question, which we'll have to wait for another week, is how ought we go about how should we go about introducing the other constraints from this isolation puzzle, which I will cover that in a different week. Do I have anybody watching at the moment? I gotta decide if I should do the video style outro or the stream style outro. I assume that I have no viewers at 3 a.m. in the morning. And also not a lot of people having stopped by for something like this. How are we doing? And, we actually have a lot of people just kind of idling. Cool. Yeah, so I will I want to commit to next week. I am almost certain I will find some way to make that not happen. But next week I will continue this with a Sudoku solver that can actually solve this puzzle without any hints, based off of this Sudoku solver that works on normal Sudoku with hints. Yeah. Okay. So I guess I should do outro stuff for the eventual VOD. What should I hit up? Stuff. Damn, it's late. things. Twitter, ping. Those are the two things I want you to know about. YouTube. Those are three things. Okay. Let me get it. Twitter. I would like to be streaming more regularly, but I in general do not stream. What I do is shit post on Twitter a ton. So you can follow my Twitter at it's Soundwave without the vowels plus an underscore. That is SN at SNDWV underscore for all kinds of fun stuff about mostly me complaining about programming while I'm working, and me saying all kinds of questionable things about VTubers all of the time. YouTube, don't currently have a YouTube. If you follow me on Twitter, I will announce it there. I will probably be streaming on YouTube as soon as I can. I don't know. I haven't really decided whether or not I'm going to stay on Twitch. But I will have a VOD channel. So if you did not understand anything in this or want to watch it again, or missed it or whatever, if you're listening to this, you probably are watching the VOD, then there's a VOD channel. And if you're not already on it, you should go check it out. Lastly, Ping. I am a founding engineer at Ping Labs, and we make a video conferencing application that you can access through the browser very easily, but it's specially designed to make it super, super easy to bring guests for collaborations or interviews or podcasts or what have you into OBS and onto your stream. If you're using something like Discord for video calls on stream, don't use Ping. It's better. You can find us at ping.gg. We'd love to have you. Those are the three things I should shout out. Man, I am falling apart, as you could probably tell. And I am also tired because it is late. It is 3:30 here. So, whether you caught me live on Twitch or you're watching the VOD, thank you for watching. Hope you learned something. We'll be back at this. I'll try to make next week. I really should hold myself to that, but I make no promises. Where we will expand this solver into being able to solve the more complex constraints of the isolation Sudoku puzzle. All right. Thank you. And